Hello guys, this is Lee Hao, and today we're going to talk about the idea of binary search. Binary search is a searching algorithm. It's so useful. It happens all the time when we're trying, not all the time, but it was used quite often because it's so useful. It helps us save a lot of time in searching. So let's talk about the most basic way of search something in an array. So if we give it a target like 3, all you can do is going through the array linearly from the very first position all the way to the end, and if we ever encounter the element, we just stop. And the time complexity for this kind of algorithm, the brutal first one, would just be O(n), which is a linear algorithm. But however, if we were given a sorted array, we can do something much better by the idea of binary search. So we have the first assumption right here. The array is sorted. We have to operate in this kind of sorted array or sorted data structure, which also applies similar kind of ideas such as tree, sorted binary search tree. And the idea here is like we shrink down the searching space to half in each round of our search. And let's see one example of how we can do it. So we were given the input. The target we're trying to find in the array is 3, and the array looks like this. In the below is just indexes. And what we're going to do is we firstly set the left bound of the searching space to the index 0 and right bound to the very end, index 6 in this array. And then we compute the middle element, middle position, which would be index 3. So right now what we're going to do is comparing the middle position element with our target. So in this first round, the middle position is 4, value is 4, and then when we compare to our target 3, we find out that the middle element is greater than our value. So what can we tell in this case? As I told you before, the array is sorted. A sorted array means everything has an ascending order or descending order, and in our case it is going up all the way. So what we can tell from this point is starting from middle position all the way to the end, it's also going to be larger than our target. That's what we're trying to find. So what we can do right now is we can smartly just deleting half of our searching space and only looking at the left side of it. So that's what's going to happen in round 2. We won't change the left bound, but we're going to shrink down the right bound to the left side, one less than the middle position in the previous round. And then we're also going to compute the middle position from now. So what we can do, what we can see now is that in array position 1, which is the middle position, we have value 2, which is smaller than our target. And in this case, what we can tell is like everything from to the left side of the middle position is gonna be smaller than our target, and we can also eliminate it. So we move our left bound from very left end to just one right side of the middle element. And we can see in this case, left and right just met each other at least position. And in this case, middle also at the same position because it's left plus right divided by 2. The middle position will have value 3 right here. Oh, it's going to be the same as our target. We found it. So in index 2, we have our value, the target we're trying to look for, and we found it. So that's the idea of binary search. When we look into the half, the middle one, in the sorted array, it's going to be either larger, smaller, or equal to the element we're trying to find. If it's larger, then everything on the right side of it is going to be eliminated. It's going to be greater than our target. We don't need to look at it anymore. And if it's on the left side is smaller, then everything on the left side is smaller. And if it's equal, then we luckily found the element. So let's look into the time complexity of this algorithm. So just as I told you before, the operation each round is like shrinking down the searching space by half. So the first time we shrink them by half because it's gonna be n over 2 and then n over 4 and then all the way to only one element. So how many times can we do this? It's gonna be the time we can divide the number by 2 and then comes to 1, and it's gonna be log base 2 of n. And in each rounds we're gonna do two kinds of operation. We're gonna compare the value and then update our indexes, so it's gonna be constant in each round. So what we have right now is 2 times log base 2 of n, and in asymptotic notation we will have O log n as our time complexity of the algorithm. And for space, we didn't allocate any extra data structure except the indexes to compute the middle position, which will be constant space too. So the space complexity for this algorithm is gonna be constant time.